Let's build a machine learning model that can recognize your handwriting. Today, we'll be building a convolutional neural network using the MNIST letters dataset from Kaggle, which has over 100,000 handwritten letters pre-split into training and testing sets. The English alphabet has 26 letters, and this dataset stores a multitude of examples of each one. In the CSV format we're using, each letter is one row with 785 columns. The very first value is the label, so whatever letter we're actually representing, and the next 784 values are the pixels of a 28 by 28 grayscale image that the CNN will learn to recognize. So now let's get coding. We start, like always, by importing our libraries. We have the basic NumPy for math, pandas for data, and matplotlib for visualizations. String module gives us the lowercase alphabet A through Z so we can turn numeric indices like 0 through 25 into actual letters. TensorFlow Keras is the deep learning toolbox that we will use to build the neural network itself. It gives us the model object, all of the needed layers, and the training machinery. Now we need to get the data into our Python notebook and separate what the model will look at from what it should predict. Right now, our data is just two big CSV files, a training set and a testing set. In this block, we load that data in and split each row into pixels of the letter and what the letter actually is. And after this step, we have our inputs and labels ready for future steps. But currently, each image is still one long line of numbers, so the model has no sense of a picture at all. In this block, we turn each line back into a 28 by 28 grid, so the network can look at rows and columns like a real image. The MNIST letters also come in sideways, so we're swapping the rows and columns to rotate them and make the letters stand up straight, which makes everything easier for the model. Also, the pixel values right now are big whole numbers between 0 and 255, so we gently scale them to sit between 0 and 1. This makes the math during training much more stable. And then finally, we're also adding a small one-channel dimension so that the data is in the shape that the CNN expects. Now it's time to fix the labels, which again is the part of the data that's classifying the letters. Essentially, we changed their formatting to be 26 empty slots labeled from 0 to 25 with zeros filled in everywhere except for the letter we're actually representing. So for the letter C, the label looks like this, and this just makes it a lot easier for the model to interpret the labels. At this point, the model is almost ready to train, but we want to make sure we haven't made any mistakes. So before we invest our time in training, we print a small grid of labeled training images. In this case, the letters are straight and upright, and the predictions are correct, so our preprocessing is safe to use. Now that we have our data, we obviously need an actual model that can look at each image and turn it into a letter prediction. So the first layer is a convolutional layer with 32 filters. You can think of this as 32 tiny neurons that can each look at one 3x3 patch of the image at a time and slide over all possible positions. It uses the ReLU activation function to keep only positive signals and outputs a feature map. The second layer is a max pooling layer that does not have its own neurons but serves as a shrink and simplify step. It keeps the feature maps pretty small while focusing only on the strongest details so the model can focus on the right details. Then we repeat this idea at a deeper level. The third layer is another convolutional layer, this time with 64 filters of 3x3, again with ReLU, so now the model can learn those richer patterns like strokes and edges built from the basic noticings from the first layer. The fourth layer is another max pooling layer that again keeps only the strongest signals and reduces the size. The fifth layer, flatten, has no neurons of its own. It just takes those feature maps coming in from the convolutional layers and unrolls them into one long vector. The sixth layer is a dense, fully connected layer with 128 neurons, each with its own set of weights that connect to every number in the vector, again using ReLU so it can find useful combinations of features that will help the model tell letters apart. Seventh and final layer is a dense layer with 26 neurons, one for each letter, using the softmax activation function so its 26 outputs act like probabilities. All of the weights in these layers are just numbers attached to connections and filters in the model, and during training the optimizer keeps adjusting those numbers so that the model becomes more accurate. Now this part is important. After the final layer, because of softmax, we're left with 26 probabilities that correspond to every letter in the alphabet from A to Z. So the fifth outputted probability is how likely the model thinks that the letter is E. And here's a summary of our model so far. So now we have a model, but right now it kind of has random weights and knows nothing about handwriting. We need a way for it to practice and improve. We tell the model how to measure a wrong answer by comparing the 26 output scores to the label, and that's the loss. Then we choose a method that will tweak the weights to make the loss smaller next time. We call this training function, it repeats the same loop over and over. Take a batch of images, let the model guess the letters, see how far those guesses are from the true answer, and nudge every neuron and filter a tiny bit so that the model is more accurate next time. After many passes through the data, the convolutional layers become better and better at detecting strokes and shapes, and the dense layers get better at turning those patterns into the right letter. And this whole process is called backpropagation. Now, to see if the model has actually learned how to read handwriting, we need to test it on images it has never seen before. So we call in the testing data and measure how often the model got the letter right, and then print the accuracy. Now we can finally use the trained model to get predictions. So we're drawing a small grid of test images and writing both the predicted letter and the true letter above it. You might notice that all of the letters here are A because the first rows in the test set are all the first letter of the alphabet. And so far, things are looking very promising. But now we don't only want to test our model on boring NumPy arrays. So let's create a function that takes whatever we draw on a scratch pad and turns it into the model's prediction live. At the top, we set up our tools. The letters variable is just our lookup table, and this is how we map a numeric output to an actual character. This predict letter function is the bridge between our drawing pad and the CNN. The first part of this function is just making sure that whatever Gradio sends it gets safely turned into a real image, and if that fails, it returns a simple question mark. Once we know we have an image, this next part is about making sure the drawing looks like the MNIST training images. So we adjust it in many ways so that our drawing is comprehensible to the model. Our drawing is in the right shape, so we hand it to the model. The model outputs those 26 probabilities, one for each letter, and we turn these into a simple dictionary because that is the format that Gradio likes. And this tiny block of code wires the function into a tiny web app. So when we launch the demo, we have effectively turned a CNN into an interactive handwriting reader. Alright, so let's check it out. Down here, I've got a sketchpad, and once I submit my letter, I'll see the model's top 3 guesses for what letter I drew. I would say the model works pretty good for the most part, but it obviously still makes mistakes sometimes. However, there's also this flag function that lets us mark an input and its prediction as flagged, so it gets saved separately and we can review or debug those examples later. And that is a convolutional neural network to recognize handwriting coded in Python right in front of your eyes. The full code is linked right here, so don't forget to save this video for when you're trying this out yourself and follow for more.